Hi, my name is Brian Slagowski, and this video is about explaining my Matlab synthesizer and digital signal processing project. So in the first part of the video, we're going to talk about the first aspect of the project, which was to create a dual-tone multi-frequency signal that represented my phone number. Dual-tone multi-frequencies are represented by this grid here. You push a button, you get a frequency tone that is comprised of the two different frequencies. So over here in Matlab, this is the first part. Here you hear the phone number, it's my phone number. It's using this array here is being thrown into the tone gen function. It's utilizing these two frequency arrays here, creating the tone, and then throwing it all into a master array, and then that's what you hear. And then we're also plotting the results of that. So we have here my phone number and my partner's phone number. And if I zoom in on this section, you can see the different profiles of these numbers here. Those different profiles are a result of the two different frequencies being thrown together to produce that particular tone. So the project continues with us having to then decipher a wave file provided to us by the teacher. The wave file is created in this Matlab program here. So it just is a random generated number, and then it gets saved down here in the .mat format, which is the exact same structuring as a wave. So then in our actual function here, this is loading in the data provided by the function from our professor. Here we are parsing out each individual section, and then we are doing a Fourier transform on that utilizing this function. We were not allowed to use built-in Matlab functions. So that function here is just a basic Fourier transform. So then we utilize that Fourier transform, and then with the find, we're able to find indexes of the frequencies in each second, and then parsing out the frequencies utilizing this structure here. With this frequency here, which represents this row, and then deciphering which frequency was the other one, then gives you a particular number. Nested if structure is all we're doing here. It's very simple, straightforward. And then after we do that, we plot out each second that we deciphered. So we plot out each portion of it, and then throw in the number that we actually are discovering into a master list, and then we're displaying everything at the end of the output. And so here we have the actual representation of everything being output. Visually, here is a 5. We have this frequency spike and this frequency spike here. You're able to use that in the nested ifs to decipher the number, and that is that. The last aspect of this project was a synthesizer, which is trying to make your computer sound like a musical instrument. I decided to do piano. So on Wikipedia, this is just a piano key frequencies. It gives you a basic formula to represent numerically each key, and then down here is the 88 key piano. Over here is the index value that you would be able to utilize in that utilized here. So then taking this sheet music here, Fiorelise is a song that I chose to do. This is a very, very basic version of the song, and I just went through, and each one of the notes here indicates a particular number on the piano key, and so having a basic understanding of that translation is all you need to utilize. And so having that, you can come over and you create yourself an array here, and this array of numbers is the index value for each particular key. This is also the keys up here. In some points of the song, there's two keys being played at the same time, so that's what the secondary array is. So this is just an array of index values. And then another aspect of making your computer sound like the actual note is you need to utilize an attack, decay, sustain, release envelope. And so it's an ADSR, and that's what helps make the the computer tone sound like a regular instrument, because there's a time here, the attack is when you actually are striking a key. There's a decay here from the attack down to the steady area of a sustain, and then once you release the key, the amplitude of the sound drops off, and that's in the release. In my particular assignment, I finished this so far ahead of the rest of the class that the professor had me add in a sine wave to my ADSR, so that's why it looks all wobbly. If you really add in a really high frequency to this sine wave here, you actually see a high wobble throughout the whole envelope. And so that's just an extra wrinkle that I had to do for my project. So here we have the ADSR over here that we're generating, and then here we're taking all those numbers from the frequency and actually creating an array of frequencies as opposed to the array of indexes. Here I am making the ADSR actually have the wobble aspect to it, and that's because that's what the professor requested, that I add that wrinkle into the project. Here we're generating each piano key note, and then we're adding it into a master list, and before we add it into the master list, we actually apply the ADSR envelope to help that particular tone period sound more like a piano key. This last one here is the very last note of the song, which is 3 notes, so I just did that particularly by itself. And then down here is more stuff where the professor wanted me to create 2 different channels, because playing 2 channels where they're slightly offset from each other helps the end result sound slightly better, and it was just, again, an added feature because I had finished the project so far in advance, and this is what it would actually sound like. And that concludes my video about my Matlab project for the synthesizer and digital signal processing. Thanks for watching.